Picture this. You're sitting right there in the exam hall, staring down a flowchart. You write down exactly what your textbook taught you about loops. It feels good. But then the results come out and the examiner gives you absolutely 0 marks. No way, right? Why? Well, because knowing the computer science concept is only half the battle. Today, in this explainer, we're going to look at Cambridge IGCSE computer science straight through the examiner's lens. We're specifically focusing on identifying algorithm processes and, most importantly, how you can stop giving away those easy marks. Look at the comparison here. On the left, we've got a classic everyday student answer. The loop repeats until it stops. Now, technically speaking, it's not wrong, but look on the right. The examiner gives this 0 marks. Ouch! The painful reality we have to face is that Cambridge examiners just don't reward what you might think they want. They're absolutely not looking for broad textbook summaries. They want to see precise scenario-based evidence. And honestly, this is exactly why ordinary revision fails. You can memorize literally every single definition in the syllabus, but if you rely on generic wording in the exam, you are actively throwing away grade boundaries. You aren't losing marks because you don't understand the algorithm's logic. You're losing them simply because you aren't speaking the examiner's language. Okay, let's dive into this. To stop losing those marks, we need a bulletproof system. Here is the mark-winning 4-step framework that turns standard knowledge into a completely examiner-proof response. Step 1, identify the concept. Step 2, extract specific evidence or data straight from the scenario. Step 3, apply your scientific reasoning. And step 4, lock the whole thing in with precise examiner wording. Seriously, keep this exact framework in your head as we break down algorithms today. It is a real game changer. Before we actually apply that framework, we need to clear up 2 concepts that constantly, and I mean constantly, trip students up when identifying processes. I'm talking about validation and verification. Validation is an automated check by the computer to make sure data is reasonable and meets given criteria. Verification, on the other hand, is a human or system check to ensure the entered data perfectly matches the original source. Knowing the difference between validating rules and verifying copies, that's foundational for any algorithm design. Section 1, Word Guess Logic, Tracking Variables in Flowcharts. And this brilliantly illustrates what they're looking for. When examiners ask you to identify processes in something like a word-guessing algorithm, they really want to see if you can track variables over time. Here, we're using a trace table to act exactly like the computer. Step 1, we start with n, which is our number of guesses left, sitting at 3. We process an input, g, the guess. Step 2, the process happens. N is assigned the value of n minus 1, so n drops down to 2. Step 3, we hit a decision block. Is n equal to 0? No. By tracking these iteration variables step by step, you are mathematically proving that you totally understand the logic flowing through that flowchart. Now, if you're identifying a process, you need to know exactly which loop you're staring at. For loops, those are for a set predetermined number of iterations. While loops have their condition checked right at the start of the loop, and repeat until loops have the condition checked at the very end. Matching the visual flowchart to the correct pseudocode loop type is an absolute classic exam requirement. You've got to have these down. So I have a crucial question for you. What is the hidden examiner clue that changes a generic answer into a top band score? In just a moment, I'm going to reveal the exact detail that transforms a borderline grade into a top-tier mark. Honestly, leaving this explainer now means missing the single most important technique examiners look for. But first, you really need to see this concept applied to something much trickier. Let's move to and see how this builds in Section 2, the temperature flowchart, finding the logic errors. Imagine an algorithm for a temperature sensor. The prompt clearly says it must accept temperatures between 20 and 30 degrees. The flowchart checks if T is greater than 20 and if T is less than 30. I want you to pause for a second and just think, why does inputting exactly 30 result in the output too high? Spotting this precise logical flaw is exactly what the examiner is daring you to do. All right, let's put on a red pen mentality and rip this apart. The fundamental error here, it's missing inclusive boundary conditions. The logic should definitely be greater than or equal to and less than or equal to, because the flowchart uses strictly less than 30, an exact input of 30 completely fails the T is less than 30 check, improperly routing the whole program to the too high output. And it's the exact same story for 20. It fails the T is greater than 20 check and routes straight to too low. The logical operators are completely mismatched with the acceptable range. Section 3, the power of test data, proving the logic. To prove this logic, we need to talk about boundary data. Listen, this is literally the most heavily tested, yet somehow most frequently misunderstood concept in flowchart analysis. Boundary data consists of test values positioned at the extreme, absolute edges of an accepted or rejected range. It directly targets those exact threshold limits to catch the greater than versus greater than or equal to errors that we literally just spotted. Let's map out these test data categories using our 20 to 30 degree temperature scenario. Normal data would be something like 25, just a standard accepted value sitting completely safely within the range. Abnormal data, that would be typing the actual word 10. It's an invalid format that should be instantly rejected by validation rules. And boundary data, that's our 20 and 30. They're designed to test those exact threshold limits and prove that the inclusive boundaries actually work in the code. Remember that curiosity loop I opened a few minutes ago? Well, here is the hidden clue that basically guarantees your marks. Scenario nouns and exact technical terms. Generic answers get 0 every single time. If the question is about a temperature sensor, your written answer must specifically mention the word temperature, the variable T, and the exact numbers 20 and 30. You absolutely have to ground your answer in the specific scenario nouns provided in the prompt. It's non-negotiable. Now, what's really interesting about this next part is how we put it all together. Section 4, upgrading your answer, the red pen transformation. On the left, we have a panicked student answer. Boundary data is 20 and 30 to see if it works. Okay, it mentions the numbers, sure, but it completely lacks all scientific reasoning. On the right, the examiner's verdict. Generic equals 0 marks. Writing to see if it works is never, ever going to cut it in a Cambridge paper. It proves absolutely nothing about your understanding of the actual process. So let's bring back our 4-step framework and fix it. Step 1, concept. We identify that we are explaining boundary data. Step 2, evidence. We pull the scenario data directly. T equals 20 and T equals 30. Step 3, scientific reasoning. We explain that it tests the exact extreme limits of the logic. Step 4, examiner wording. We assemble these pieces into one precise, bulletproof sentence. And here is the stunning result. Read this carefully. Boundary data tests the extreme limits of the valid range. For this temperature check, the inputs 20 and 30 must be used to ensure the inclusive boundaries are accepted. Wow, this is visually and logically perfect. It uses the exact technical term extreme limits, the scenario data 20 and 30, the scenario noun temperature check, and proper reasoning with inclusive boundaries. This right here, this is exactly how you secure top band marks. So, the crucial point is this. Surviving Cambridge computer science algorithms isn't about rote memorization, it's about structured application. Let's quickly recap the whole shebang. First, identify the specific process. Is it iteration, selection, or input? Second, act like the computer and track variables step by step with trace tables. Third, the golden rule. Always, always use scenario nouns in your written answers. And finally, validate inclusive boundaries using specific test data. But you know, a terrifying reality remains. What if you do all of this, but you still lose out? It happens to thousands of students every single year because of dreaded examiner report mistakes. These are unseen traps that you don't even realize you are falling right into. You absolutely must understand these unseen examiner report mistakes if you want to survive this exam. To protect your grades, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations, and I will see you in that next explainer, because you really have to ask yourself what happens when your perfect logic still gets a 0.